And now let me introduce you to Bim Kim, who is a senior research scientist in Google Brain. She got her PhD in MIT in Boston, and she works in interpretable machine learning. Maybe some of you have seen her already, giving several tutorials and organizing workshops in different machine learning and AI conferences around the world. And also probably you know her seminal work, the TCAP, which actually got a UNESCO award recently because of the breakthrough research she is doing. She's also a very active researcher in the machine learning community and active in initiatives like the Women in Machine Learning. And I have the opportunity to be in several places with her, and it's always an honor to have the opportunity to listen to her talks and ideas. And without further delay, Bim, all the stage, Zoom stage is yours.
Thank you. Thanks for the generous introduction. I'd like to first thank the organizers for inviting me. It's a lot of work to organize a virtual conference, or let alone the actual physical conference. I'm really excited to give a keynote here today. This is ECML, was one of the first conferences that I attended as a grad student. So today I will be presenting work with a lot of great people inside and outside of Google. So 2020 has been quite a year for everyone, to say the least. There's pandemic that's going longer than I thought, systematic bias, global protests, and if you're in US like myself, you have to deal with this guy too. Personally, not a fan. And we can talk about this for hours. And I'm sure many of you had challenging times during this pandemic, and whatever difficulty that was, it is very real. I don't know about you, but this global crisis left me feeling fortunate that I have a job, but I keep wondering where this world is going. I also became a mother during this pandemic. I have a 2-month-old son, and who might cry during this talk, and you will hear him. And this made me think, what kind of world did I bring him into? And mostly I wondered if there's anything I can contribute the world that my son will live in. So in this difficult time, lots of folks are struggling. One of those folks are small business owners, like restaurant owners. And I didn't know anything about running a restaurant prior to this pandemic. I still don't, but I read articles that did numbers on how close they're meeting every month on their budget. They barely make ends meet every month. It takes a lot of money to open a restaurant. You have to buy equipment, ovens, hire staffs. And even if restaurant is closed, you have to pay rent and bills. And this pandemic made it harder for them since they had to quickly adjust, and many already ran out of business because they couldn't. And it turns out that quickly adjusting required computer skills in 2020. There's this pizza place in Seattle that I really like. This is one of this out of nowhere place, but it's a legitimate gem in town. This place is pretty pretty much sit down place where they have great cocktails and pizzas from fresh out of the oven. So this pizza place never participated in online ordering service or Uber like Uber Eats. But when pandemic hit, they're only allowed to have takeaway. They needed to set up an online ordering service. Now they're experts in pizza making, but not in computer skills. But they had to set this up fast. So this is a real story. A very kind friend of mine, another loyal, much longer time customer of this pizza place, who happens to be a software engineer, just jumped in and helped them to set this up quickly. So they are able to continue their business to this day. So why was this hard to set up? Well, making an online ordering service isn't part of a skill set required to become a cook or restaurant owner. And not all restaurants are as lucky to have my friend as a customer. But it turns out in 2020, restaurants not only have to have good food, but also need computer skills to stay in business. Otherwise, you have to spend money to hire someone in already tight budget. So I think in 10 years or so, 2030, when machine learning is being used for a lot of things around us, a restaurant owner or other small business owners may need to also know machine learning to keep up. Perhaps building a recommendation machine for your pizza restaurant to predict what kind of pizza will be popular this summer. In fact, this is already happening. Have you ever visited a website, maybe family-owned business, small website, and they're trying to recommend you something to buy, but you bought this cheese and they're now suddenly recommending you, oh, now you need this brick oven that is specifically designed just to make pizza. And by the way, it's a couple of $1,000s. And why was ML hard to use for a restaurant owner? Right now, one way to use machine learning is hire one of you in the audience. Someone who can build model and customize it for your application. But you are all very expensive, much more than what they can offer as a small business owner. And budget is already tight. So how can they use machine learning without having to hire someone? There are many ways. We can have a model build automatically from some training data, but it has to be customizable because nothing's going to work just magically out of the box. And it also has to be interpretable to everyday people, like the owner of a pizza restaurant, not just someone who were fortunate enough to get PhD in machine learning. Only then the owner can make this model fit to their needs and use it effectively, maybe by interjecting their insights, their expertise. So this talk is about interpretability for everyday people. How to make machine learning model more usable by everyday person who may not know computer science, let alone education. But making progress in interpretability is hard. You may ask, well, it's just a matter of defining the problem in math. Why don't you have an objective function mathematical definition of interpretability? Then it just becomes optimization problem. Well, there's no mathematical definition of interpretability. You can ask psychologists who's been trying to study humans for centuries, and they can attest you that this is probably close to impossible. So it is a very hard problem, but research problems aren't easy. Easy problems aren't fun. So, but how do we know that we are making progress? Here's one way, one path for progress. First, we are going to check where we are going, what kind of toolkits we have, what methods we're developing to decide which direction we're heading. If a whole field of interpretability is in this sailboat, we need to sail in the same direction together in order to go some meaningful direction. And then at each step, we want to question ourselves how we can do better and over again. So this talk is about first seeing where we're going by revisiting popular interpretability method and challenging them. And I'll propose one way to improve interpretability for everyone. And we will revisit that method over and over again to see how we can do better. So first, where are we going? Let's focus our discussion today to post-training interpretability method. What's that? Well, it just means that you have a model that is trained, you can't change the model. But the goal is, given this fixed model, you want to find the evidence of prediction. In other words, why was this picture predicted as Junco bird? Now, one of the most popular method is called saliency maps. And the saliency map often based on first order derivative of probability of the class with respect to every single pixel. So you get, at the end of the day, picture like this, where purple pixels are important, this one, white pixels are important. So you kind of get a map of the picture. So this sounds good. So the promise of this method is that these pixels are the evidence of prediction. Then we can flip that around and ask some sanity check question. So you said this is evidence of prediction. So if I change the prediction, then explanation should change because this explanation is a function of prediction. In an extreme case, when I make prediction completely random, then the explanation should really change. So we put that in a test. We got this model fully trained superhuman performance image classification network, and we got many, many images and feed us images and got saliency maps. And then we took the same network, we copied it over, and we started randomizing the weights from the top layer into top 2 layers, top 3 layers, top 4 layers in this cascading fashion. So remember, as soon as you randomize any weights, your prediction will become random. So you would think that the explanation should change. It doesn't. And you might say, well, these two pictures are technically not identical, just a little darker there. But remember, the whole point of any interpretability method is for human consumption. And as a human, I can't tell you whether I'm going to draw a different conclusion in these two pictures. The belly of the bird looks important in both the pictures, and a lot of highlighted parts seem similar to me. So we did this for many pictures for entire layer in cascading fashion. So this second column is just logic layer randomized. Second column, top 2 layers randomized, all the way to last column where entire network is randomized. And we tested many different methods, some of which are my work. And we show that, yeah, a lot of these methods actually don't really change their message as the prediction gets randomized. So shocked by this result, we tested another thing. So now, what if we train a network with random labels? Now, when we train the network with true labels, then you can see the MNIST digit 0 showing up. That makes sense. But even when we train the network with random labels, it seems to show, some of the methods seems to show that it might have learned digit 0, which it didn't because it was random labels. And interestingly, the vanilla gradient seems to be doing reasonable thing, at least what I expected to see. But funny thing is that a lot of these methods are based on vanilla gradient. It's just bells and whistles on the top of vanilla gradient. So since this work came out, it has become one of the go-to tests for pixel-based interpretability methods. And I'm an area chair and oversee many interpretability papers and many conferences. And I can share some of the iClear reviews because they're public. I have seen reviewers asking if the paper had run this test. Many authors ended up running this test during their review process. There has been also a number of great work to make better tests, which is exactly what we should do, or to build methods that ensure passing this test. So that's all great, but how did we get here? For many years, many people worked on, including myself, worked on saliency maps. But how do we not know until to this day we ask this sort of very simple question? I think it's partially due to confirmation bias, which is something that I see over and over again in my work. What is this? Well, when humans sees something that they expected to see, they like it, they think it works. There was a picture of a bird, you expected to see a bird in the explanation, you saw a bird, and you liked it. And so this is important evidence that just because it makes sense to humans doesn't mean that it works. And remember, just because you pass this test doesn't mean that you have a working method. This is the bare minimum question. This is just a start of making a lot more tests that all of which you have to pass in order to make a claim that your method is working. But some of these methods have shown to be useful for certain human tasks. So I think there's something useful in these methods. We just don't know what they're showing yet. And to find out more, we have to do more studies. So how can we do better? Given this, let's learn some lessons and figure out if there's a way to make this method a little better. Again, our problem is post-training explanation. You have a model and you want to say, we want to ask, why was this, say, popular pizza? If your model takes a pizza picture and outputs how popular it's going to be. Let's look at the saliency map of this pizza picture to help us think, what do we really want to ask? So as I stare at this saliency map, it looks like there's some bright pixels on the tomatoes and on the crust. So as a business owner or a pizza restaurant owner, if I were one, I'm curious, is the tomatoes more important or the crust? Because we know that crust is a very important part of great pizza. As I stare at even more, I see these wine glasses being highlighted. And of course, yeah, what you're drinking when you're eating pizza is very important. But was it more important than pizza toppings? Because if it were, then I better put together some new cocktail menus rather than adding new pizzas to the menu. And is this true only in this picture or all popular pizza pictures? Is it the general pattern? The problem is that I can't express these concepts as pixels, especially across many pizza pictures. If you had these concepts when you're training the model, wine, tomato, and crust, then you can assign that as an input feature and saliency map can get you the number you want, the importance number. But you didn't. We already trained a model and you just thought about these concepts and you are forming hypotheses in your mind. So wouldn't it be great if we have a way to quantitatively measure how important these user-chosen concepts are? So this is exactly doing that. It's called TCAV, Testing with Concept Activation Vectors. This is providing quantitative explanation for a concepts that you came up after the training that is important for a prediction. So for instance, as an owner of a pizza restaurant, I'm curious, how much importance does each topping carry for this popularity classifier? Is it the tomato, is it the cheese, or is it the wine? A running example for this talk is going to be zebra. Our question is, how important was the striped concept to this zebra image classifier? So using this, I'll explain how this works. First of all, you might ask, oh, okay, well, this concept business sounds good, but how do you even define concepts? We do the simplest possible thing. We define concept using a vector called CAV, concept activation vector. And to learn CAV, you need a couple of ingredients. You need examples of concepts, so some striped pictures, and some random images for the reasons that will be clear soon. And of course, you have this network that you want to investigate. And we assume that you have internal tensor functions. So this f of L takes input image and maps it onto activation on layer L. Once you have all those ingredients, you simply train a linear classifier to separate concept activations from random activations. And the vector that is orthogonal to this classifier simply is the CAV. And what is this vector? Well, it just means that a vector direction from random activations to concept activation. And of course, this is not a new idea, having a vector that is semantically meaningful. And there are lots of ways to fancy it up. You don't need linear classifier. You can do nonlinear, and other methods are also available. So cool, we have this vector. What are we going to do with this vector to get that quantitative measure, the TCAP score? It's also pretty simple. To get TCAP score, we're going to take directional derivative of the prediction of a zebra with respect to that vector we just got. So what this derivative does, intuitively speaking, not literally, is if I change this picture to be more like the concept or slightly less like the concept, how much would the probability of zebra swings? If it swings a lot, it's an important concept. If it doesn't, it's not an important concept. Then we get that number for many zebra pictures. And we use this equation to get a TCAP score that is always between 0 and 1, What is this equation? Well, we're just simply going to find what's the fraction of zebra pictures that give you positive directional derivative. So you have 100 zebra pictures, 80 of them came out positive directional derivative, then your TCAP score is 0.8. And of course, you don't have to stick to this equation. People have been customizing this to fit that such that it can fit their bill. So that's all good. It's pretty simple method. And you might say, yeah, that is pretty simple, and you will be right. I love when an idea is so simple but yet powerful for interpretability for everyday people, as I will show you soon. But one question might linger in your mind. So you talked about this vector, and this vector lives in a very high dimensional space because its activation often 100,000 or more. And thanks to discovery of adversarial directions examples, we know that things are a little funky in high dimensional space. All our intuition is out the window. So is this CAV legit? And that's what we're going to talk about next, how we can do better by confirming that these CAVs might be legit. So the point is guarding against spurious CAV. We just want to make sure that this CAV didn't return high sensitivity by chance. There are lots of different ways to do this. Here's one quantitative way to validate. So remember when I talked about this CAV, we learned this CAV by training a linear classifier against many random picture activations. These are random, so you can put any random pictures as many times as you want. And each of this experiment is going to get you one CAV. And after a lot of experiments, you get many, many CAVs. And for particular target of interest, in this case, zebra, you will get many, many TCAP scores. And now you can consider these TCAP scores as samples from a particular distribution. Now, if this is some consistently striped star error important, then you might get some Gaussian distribution, maybe mean on 0.7 and whatnot. And then you can compare this distribution to TCAP score distributions with random CAVs, where random CAVs are, this is random and that's random. And then we run t-tests, and only when it passes this test, by which I mean the two distributions are statistically significantly different, we use this concept. So all the results that I'm about to show you are only the concepts that pass this test. If we didn't pass this test, that means, well, you, the user, thought this concept is important, but it turns out that it wasn't. So here are some results. I'm going to cover partially. Sanity check experiment is my favorite, but it takes a while to explain, so I'm going to pass to the next one. We tested Inception v3 and GoogleNet, one of the most popular image classification network. And we used many sets of concepts like color, red, yellow, blue, green, race, and even objects. So let's look at fire engine class. Fire engine class, it looks like red is important. Green was also important because fire engines are often sitting on a grassy field in these pictures. So this makes sense, unless you're from Canberra, Australia. I don't know if there's anyone from Canberra, Australia in the audience, but in Canberra, Australia, fire engines are yellow. And there's actually really a reason why they should be yellow, because they're more visible at night, among other benefits. So your model might contain some geographical bias. And also we discover other biases that were previously qualitative findings in prior work. And here are some published work from Google researchers on image model to detect first the image model on the left to detect sensitive attributes. And on the right, they use TCAP for language model. This model classifies toxic comments on online platform, which shows that this method can be also effective, not just image models, but also language models. We also worked with domain experts, particularly medical experts, on this particular condition of diabetic retinopathy. DR is treatable but site-threatening conditions. And we have a model that's published from Google that achieves high accuracy of 85% to predict the level of DR, the severity of DR. So we wanted to ask, well, is this model use concepts that human doctors would have used, the diagnostic concepts that they would have used? So to answer this question, we first went to a doctor and we asked her, tell us what kind of concepts that you expected to see for this level, DR level 4, which is the most severe level of DR, and for also DR level 1, very minor level of DR. And also tell us what concepts that you do not expect to see that would conflict with your expertise. And we used these concepts to use TCAF to ask the same question to the model. For a class that has high accuracy like DR level 4, we show that, yes, they are consistent. The green concepts are high, red concept is low, that's good. But when the prediction score is low, like DR level 1 or mediocre, it turns out that model was using concepts that are inconsistent with doctor's knowledge. This concept, HMA, is a type of hemorrhage in the blood vessel. And it turns out that DR level 1 was often confused with DR level 2. And DR level 2 had a lot of HMA concept. So that this TCAP was reflecting some of the truth about the model. So perhaps we can use this method to double check a model against domain expert knowledge before deployment. So that's cool, but what if I don't have concepts? I was lucky to have an access to a doctor who gave us these medical concepts, but what if you don't? Can we automate this? That's what we do next. What if we don't have concepts a priori? Can we automatically discover concepts? This is work with intern Amirata, who was an intern back at time, now at Stanford. So the idea of this, the goal of this work is you have this trained network, but you don't have any example concepts, or maybe you don't even have random images. The idea behind this method called ACE, Automatic Concept-Based Explanation, is pretty simple. First, you're going to take training images. You can actually use other images too, but same distribution is better, so we use training images. And you take this image and segment these using superpixel method. What superpixel method does is segmenting the image in sort of roughly semantically consistent patches. We do this for one picture, we do this many times. So we will call these guys patches, and we feed these into the network as if they were input images by blowing them up, and we cluster them using some smart clustering segment and outlier removal. After clustering them, we score each cluster concept using the TCAP score. And it's okay if you have many clusters, because perhaps the only thing that you're interested in are the highly scored concepts, or maybe very low concept score clusters. Now, the first question, though, you might ask is, look, this is pretty simple, but how do you know that the concepts that are discovered are interpretable? The only way to check this is by doing human experiments. So we did 2 human experiments. First one is the intruder test. What this is I give you 6 pictures, and I'm going to ask you what's the one picture that's weird, the odd one out. And we compare how well humans do on that task with our discovery concepts, compare that to human labeled data set. And we show that our discovery concept humans can do as well. In the second test, among other things, we ask humans to name the concepts. So they will see these discovered concepts, and we ask them, if you had to put a word on it, what would it be? It turns out that 56% of participants describe it with the most frequent word or its synonyms, and 77% describe used one of the 2 most frequent words. And this is quite surprising, was quite surprising to us, that it shows that our discovered concepts are consistent enough that different humans, Turkers, can put a name, use the same word to name the concept. So now we want to also confirm that these are not just interpretable, but they are important for the model as well by doing addition and deletion test. Addition test is you start with by putting the top most important patch, and then top five patches, top 10 patches, and you see that the prediction accuracy increases if you sort your patches from the most important to least important. And if you do the opposite by adding least important, that accuracy increase, the delta is smaller. And of course, random is here as a control. You can make the same conclusion by doing the deletion, deleting the top most important, top 5 most important patches, and so on, and you see similar patterns. Let's see some qualitative results. Look at this class. Here's the train classes. Here are 3 pictures of trains. And one of the most salient, fourth most salient concept turns out to be the pavement. And this pavement has particular character. It's tiled. I don't think this is common in every country in the world. There are some part of the country, maybe Korea, we might have just a concrete floor instead of tiles. So this might not work in Korea. Another interesting discovery is having this dumbbell class, but most salient concept turns out to be the human who are holding these dumbbells, not the dumbbell itself. And more problematically, these humans who are holding dumbbells have typically light skin. So depending on what you're trying to do, you may not want this model. So that's cool. Now we talked about discovering concepts, but how do we know that when I can stop? Do I have enough images? Do I have enough concept clusters that we discovered? So that's the thing. I see somebody raise their hands. I will let Isabel decide whether we want to take the questions now or not. Stop me whenever you would like.
So I think it's best if we wait until the talk is over, because also the hands show up and disappear very quickly. So right. I might lose the people in the process.
All right, sounds good. We will ask Huba to help us the questions later. So this is automatic discovery is good, but how do we know when to stop? Can we discover complete concepts? This is work with Chikwan Ya, who is a CMU PhD student, intern at the time at Google. The key idea is to decompose activation space into concept vectors. And the hypothesis is that if the concept vectors can span the activation space, then we assume that the information in neurons can be expressed in terms of these concepts. And we learned these concepts for all classes, like whale, zebra, and bat, and not just one class, unlike ACE or TCAF. So here are some details. We first use ACE to segment the images and have those clusters. And these clusters form vectors. Then we measure using some variation of Shapley values to see how important these concepts are. Now the definition of completeness is here, which I'm not going through in detail, but why this is particular completeness definition? Well, because under simple assumptions, this metric is equivalent to top K PCA vectors. So we get all the nice properties and a lot of work done on PCA for free. So here are some quantitative and qualitative results. Here is quantitative results. Blue line is ACE that shows as I add more concepts, I get more and more completeness. So monotonic increase, that's good, but not quite a quick conversion as much as I thought, or as much as we hoped. The k-means, yellow line, is pretty good from the get-go, But we know that k-means have no guarantees that these clusters will be interpretable, and ours are up here in green. K-means always surprises me. It's almost always when I use them, it's just surprisingly good. And here's some results for 2 classes, zebra and lion, and some shared concepts. So we so far talked about having quantitative measure of concepts, and we talked about how to automatically discover them and how to automatically discover complete concepts. But what if we flip this around and build a model where this decomposition that we just talked about is built in when you can build a model? In other words, in cases where you have concept labels for training data, you can train a model from scratch such that somewhere in the middle, there is a bottleneck that distills all neurons into concepts. So that's what we did. What if you build a model from scratch? This is work with Pang-Wei Go and others at Stanford. So say that you have some concept labels for training data. So you know zebra tree concepts are 30% important, stripes are 45% important, and so on. Then you can train a model to minimize that concept label, ground truth concept label, as well as the prediction label. And remember, you don't need concept labels at test time. You just need it at the training time. So first thing first, now you're building a model that are interpretable. I heard about this trade-off between interpretability and performance. So is the performance impacted? No. In fact, a lot of cases, models that I worked on, if you put enough care and work, enforcing interpretability does not compromise performances. And here we again see that evidence. 3 different ways to train the same model. We see the error rate lower, error rate similar or lower than the standard one with no bottleneck. Now, another great thing about the bottleneck model is that you can interact and control the model. So for example, if you don't think trees or lion concepts are important in predicting zebra, then you can zero out these concepts and feed forward, propagate to get a new prediction for zebra-ness. And this controllability is particularly useful when we have a domain expert. We can incorporate their domain expert knowledge. Perhaps machine learning model thought that symptom X was important, but doctors know that it is not important. Then you can incorporate this at test time. So we did exactly that using an arthritis data set. This is a medical data set that came with concept labels. So we replaced concepts with the true concept, predicted concept with the true concept. Supposedly that's what doctors thought. And as you can see, we saw quite a bit of increase in accuracy. These 3 ways of training that model compared to the control case, the blue model or blue line. Enabling interaction between experts and machine learning model is an important topic, and this is just one of many ways to do it. There are lots of great work, particularly done in HCI, that we should pay close attention to. So cool. What does, so that's cool. We had talked about completeness and now we all the way came to building a new model. But what does this interaction trying to really incorporate is sense of causality? Did the symptom X cause the diagnosis? Well, we know that we can properly measure concept causality. We have, given the existing model, there exists a definition. So maybe we should do that. And that's what we did in the next segment in causal concepts or causal TCAF. This is work with Yash, Amir, and Uri when Yash was intern at Google. So the basic idea is let's stick to the principle and calculate ATE. And how do you calculate ATE is you do operations on concepts using generative model. And here's just vanilla definition of ATE. And for example, it looks like if you have a gender classifier, say F, and you're curious whether glasses concept is important whether that caused this classifier to classify gender in one way or another, then you first have this picture, the original picture, predict the gender, and you use a generative model to remove glasses, and you calculate the difference between the expected value. And there you go, you have the ATE. So this is straightforward. Why is this hard? Why is this a paper? Well, the challenge is to make generative model good enough to measure the good ATE, or cake that we call it in this paper. We're not trying to use this generative model to generate high quality images, just want to measure ATE. So we trained many models, VAEs, GANs, you name it. But here are two ways that we find most effective. First, you can just use the decoder, where you use the sampled Z, the latent distribution. By doing so, you're testing general distribution that are learned by this generative model. Another way is to use both encoder and decoder by using the particular instance, in this case, some red bar picture. And by doing so, you're testing particular populations. So for example, you just want to test the causal influences on incorrectly classified pictures. And the important thing here to claim that this method is useful is compare against ground truth. So we tested through many data sets, but here's one data set, natural images data set, where we have scene pictures, and we copied and pasted an object, in this case, a dog or a cat. And by doing so, and we made up this data set, so we know that this is serving as the perfect generative model. And that cake measure using that generative model is here, and we compare that to our measure, the decoder measure in that cake. And as you can see, often decoder cake works better by closely following the ground truth cake. Whereas the baselines aren't really close to ground truth, especially where we intentionally introduce high correlation between concept and classes. So far I talked about, so today I talked about the technique called TCAV and many ways to make that work better. We talked about CAV testing, we talked about automatic concept discovery and complete automatic concept discovery, along with building a new model that had those concepts built in, concept bottleneck models, and causal concept measures. All this work has their code published open source, and TCAV code is located in that GitHub. I was so delighted to see many folks outside of machine learning community using this method to communicate machine learning results with experts. Here, Carrie Kai's work on the left is using part of this work to help doctors find more diagnostically relevant images. Here, these are medical concepts that doctors can increase or decrease and see the different images. Here, TCAV was used for radiology and breast cancer, where TCAV was extended to regression. Eric from Aerospace Corporation also used TCAV to explain storm prediction models by using like eye of the storm concepts and many others. Now, this method is now used by Google teams and products. So Sundar talked about this work at his Keynote Google I/O 2019, and UNESCO kindly gave us an award for 1 of 10 cutting-edge digital innovation with the potential of profound and long-lasting impact. So we can't stop here. We have to keep going. Let's think about what we can do better by looking at some limitations of this method. Concepts have to be expressible using examples. If you have two concepts that are completely correlated, it always occurs at the same time, then it might be harder. It's not impossible, but it might be harder to use this method. If the concept is abstract, like love, also hard to use this method. Not yet. The discovered concepts that we talked about don't have names. So perhaps we can co-train some language model to put a name on it. It looks like that is possibility based on our human experiment, but we don't have yet. So right now you have to look at the examples, example patches in the case of images. There's almost always the gap between how humans view a concept versus the concept that machine learned. Because we are so primed to look at this world in a particular way that we might overlook particular correlations, but machines might really learn that correlation. And I think to bridge that gap, one of the great ways to bridge that gap is, for example, using these interfaces designed by Carrie Kai, having humans play with machine learning by changing things to help them build better mental model of what this machine learned. There are interactive interfaces that we can work on to make it easy to collect concept examples too. Before I go, I want to talk about things that we should keep in mind as we go forward. Evaluations, very important. Sanity check questions are just a start, and there should be many more tests that we need to build up as a community as a test that you should pass whenever you're publishing your papers. And doing so, if we have a ground truth data set, that will be helpful. So we published this data set benchmarking attribution methods for image-based models where we know where in the picture the model looked at so that you can use this, and we propose a couple of metrics. And this is one of many work, many testing, many benchmarking that we should be doing as a community. Evaluate with humans. Remember, the whole point of doing interpretability is for human consumption. If you don't check with your final customer, you don't know if your method is working. So we should do that whenever we can. And remember, humans are biased and irrational. Unfortunately, or fortunately, every method will be developed by a human, like myself, and we are all biased. So let's keep that in mind, take that into account as we develop a method, making tests, or doing evaluations. Backend alone, a smart algorithm alone isn't gonna get us the success. We need to design the right interaction in order to get us to the final goal. And looking at work coming out of HCI is very important. And let's keep checking that if we're going in the right direction as we follow in this journey together. In this difficult time, I feel incredibly fortunate that I was educated, and I'm educated in computer science at the right time so that I can safely stay home. I'm going to guess that a lot of you also fortunate in similar way. In 15 years or so, my son will be 15 years old, and he might ask me what I did during those global pandemic, this unprecedented global crisis. And I will tell him that, oh, well, I was changing your diaper, I was feeding you every 2 hours, and you were attached to me 24/7, except for the time that I was giving ECML Keynote. But I hope I can also tell him that I worked towards democratizing machine learning technology, because back then it was only available for a very small circle of privileged people. Thank you.
Thank you very much, Vin. So let's start with the questions. I have a couple of questions in the WOBA. I believe the first one is by Christian. So Christian, if you are in the Zoom, I can see you. I can unmute you if you raise your hand, otherwise I can read your question. Let me see. Christian? Let me see. I'm trying to unmute him, so this is a bit... Hi, Christian, are you here? Okay, so it got muted again. So maybe I can ask myself the question. So it seems quite important to have interactive explanations and the communication. You saw in your talk the example where sometimes having this interaction is not as easy. Do you have an idea of how interactive learning or how we can make progress further progress in that direction, or what is the reason why this interaction might seem not as doable as we would like it to be? Mim, you are muted. Let me see.
Yep. Am I unmuted now? Cool. I think this is a great question. Interaction and closing this loop between humans and machines has been my long-time goal, and I would really want to see a lot more progress, and we have been making a lot of progress. My theory, or why the reason that I've been focusing on just one direction, if this is human, this is machine, and one direction of communication from machine to human, and instead of before closing the loop, is because I just wanted to make sure that we are going in the right direction first in this communication, because if this is wrong, then the closing the loop is also going to be wrong. So that's sort of my rationale behind my heavy focus on this direction only. It's incredibly important direction to study. I want to emphasize lots of great work coming from HCI. They study in many important applications like medical and science, how this interaction should be accompanied. And active learning and other ways to deal with this in the back end is also, of course, well studied in machine learning. Lots of great directions, not many answers.
Thank you. I have another question about CAP. Actually, a participant is asking whether you can use CAP, or you believe you could use CAP for detecting out of distribution samples. And so how would you think we would be able to do so?
Oh yeah, we did this in the original paper, and I was very excited, but we put it in the appendix. I think it's possible. I didn't follow through there, but the way that we did it in the original work is if we have, let's say, 10 classes, like, and one of them is zebra, you can find the distribution of concepts of that class zebra. So maybe stripeness is 80, trees are 30, whatever. And we tweak that network, we tweak the network to make adversarial example. So its prediction is no longer not a zebra, but to human eyes, it looks like a zebra. Then we show that the concept distribution, there's a huge change. Your pixel or prediction might not change very much, but the concept distribution changed a lot. And based on that idea, we thought, oh, you can also detect out of distribution change, distributional shifts. If you have what normal concept distribution should be for your classifier, you can just keep checking on that as you maybe update your model, as your input distribution changes, and follow through. And if that changes, you just, okay, well, something is changing. Let's put that aside, turn it off, and do more testing. That's one of many ideas.
Thank you. So moving to the next question, we have here whether you believe we could generate summary text out of explaining saliency maps. Whether we can give explanations, I guess it comes in the direction of giving explanations not only as images, but transform that into text.
Yeah, I briefly mentioned that. I wish we can name automatically discovered concepts. I think it is probably possible. However, whenever I think language is difficult. Whenever we introduce language, that one word might mean different things to different people. We don't have that problem very much in images. So what I'm saying is there's that extra challenge when you decide to introduce language in naming something. You have to also carefully think that through as well. I think it is actually possible for ImageNet models where we have plenty of training data for training language model for, to name human, zebra, trees. It would also be, though, harder for domains where you don't have that much data, like medical domain and other scientific domains.
Okay, maybe a follow-up question about that by myself is whether you believe that we can generate concept-based explanations for other domains beyond images. For example, the one of text, where you might want to explain why a text was classified with a given sentiment or similar.
Yeah, we've done that. Actually, not me. The Ben Hutchinson at Google has done that for a language model, and we've internally also done it for BERT model. So what Ben did, this is published work, is took the toxic classifier model. So given an online comment to you to classify whether this is toxic or not, and he tested whether LGBT concept had played a role there. We don't want LGBT concept to play a role, and he was able to distill that it was playing a role initially, but once you debiased the model as best as you can, that concept significance has been increased.
Thank you. So we have actually quite some questions. I'm trying to follow all of them, but I might miss some. If I don't find them, vote for them so that they show up again on the top. A participant is commenting on how expensive and time-consuming might be to have an expert, a human expert, to help you validating your concepts. And he's also asking whether we can find a proxy for evaluation without, for example, needing a doctor supervising our methods.
Yeah. We Finale, Dosh Velez, and I wrote a paper about this, that you can use proxy because, I was a grad student too. It took me 3 years to get one domain expert, and it is very difficult to do in many areas. So in that paper, it's called Towards Science of Interpretability, Interpretable Machine Learning. We do suggest exactly what you're saying. We suggest you can do proxy by designing a proxy task that's similar to what domain experts would have done. So if it's diagnostic test of classifying cancer level, then you can replace that with classifying something else that normal everyday person can do. And that proxy task, you can test it with Turkers, where you have bigger population that can help you and more affordable. And by doing that, you can at least make progress, right? But in my opinion, before deploying a model, you do have to absolutely check with domain experts. If you're deploying, especially in high-risk domain, it is, I believe, our responsibility to get the domain expert to validate that model.
A follow-up question there is, how do you think that such proxy might help evolving the interpretability field?
Oh, say it again, sorry.
So once you get the proxy for the human, do you think we can use these proxies actually to help the interpretability model to improve as well?
Oh, interesting. Yeah, I think this loops back with the interaction question earlier. Yes, absolutely. There are some fundamental interaction or explanation that you can improve based on the results. What are they getting wrong and why are they? And just keep asking how you can do better.
I'm trying to come back to the questions because the order keeps moving.
And if you have questions that I didn't answer, you're welcome to message on Huva, and I'll do my best to answer them.
So I think if you have time, maybe we can use a couple more minutes, given that there are no other events right after your talk, to answer maybe 2 more questions.
Sure.
The first one would be if you have any thoughts on quantitatively comparing 2 explanation methods, for example, given 2 saliency maps or 2 TCAF model sets of concepts, how do we quantitatively decide which set is better?
Which set is better?
Yes, for example, if you have 2 TCAF methods and they give you 2 different set of concepts, how do we pick one over the other?
I see. I like this question because it gives another opportunity to repeat the ground truth-based evaluation that I talked about. I think you need ground truth data set, and there aren't every ground truth data set for each application, but we published one for image data set, benchmarking attribution method, and we open sourced it. If you Google GitHub benchmarking attribution methods and my name, you will probably get to that data set. For images, you should test that. Then you have definitive answer to which one is showing you the truth. Now, it's not a certificate that because you get the better score in this particular data set, that means it's going to work better for you in real life. No, it's not. Then what you do is, again, a little expensive step of getting the humans to validate your results. That's your golden goal. That should be your target whenever you cannot get there. For other domains, you can create that kind of data set too. If you have a look at our benchmarking data set, it's actually quite simple to make up the data set for your domain, language and other domains. So I would suggest that that's the best way you can do, if you
can. So, and to finalize, I'm gonna ask a kind of a more practical question. So they say that deep learning is known to have a terrible carbon footprint. For example, the transformer is multiple worse than human during life. So I guess we are talking about ecosystems. And the question is how bad these interpretation methods are on this regard.
Wait, I think I need to read this. How do I? Oh, I see. Deep learning is known to be a terrible carbon. Is multiple worse than transformer is a multiple worse than a human life? How bad are these? I'm curious what you mean exactly in this axis. Do you think that is like a technical debt we're creating, or do you mean literally a carbon footprint?
We have some people raising their hands, so maybe we can just to finalize open.
Yeah, let's.
Hi. Yeah, that was my question. Yeah, I mean, I have heard a talk from a researcher, but I tried to search to find it in the internet, but I don't find it anymore. But it was at a prestigious conference, that is what I remember. And she said how much carbon emission the training of such an NLP transformer model produces during training, simply by using up energy and all this kind of stuff. And the result was that it was compared not to the human lifespan, but to 1 year of a human. But I calculated with an average of 80 years lifespan of the human, that it was still like 3 or 4 or 5 times, I don't remember, worse than what a human average has in emissions. And that is pretty bad. I mean, if we discuss things like, should I get children because of the carbon footprint they have, and people are discussing that, right? And these kind of ethical questions. But then as a machine learner, I train like a multitude of transformers. I mean, I can have as many children as I want, as long as I'm not a machine learner, really. So that was that was pretty shocking to me, to be honest. And your methods seem pretty elaborate. Now, I have been a big fan of elaborate methods until I read this stuff, and I'm like, okay, maybe elaborate methods are actually not the way to go in one way or another.
I see what you mean. So everything that we do, this is a philosophical question, and I like these. Everything we do is cost-benefit analysis, right? If what you're doing causes cost, but your benefit that it's creating is better than the cost, then it justifies, one might argue, that it justifies the mean. I think similar goes to this purpose. Say I mean, this is really like Peter Singer type of discussion, but if we believe that a carbon footprint of one person's on our lifespan is better than, say, having a machine learning model that can serve a whole community where there's no doctors, and now a machine learning model can save these people, then one might argue, well, you have to weigh this in too. Separate answer for your elaborate method question. It's actually not that elaborate. I love how this method is very simple, and relatively speaking. the directional derivative is actually linear operation. So you can completely parallelize and it's not that involved. The most computationally expensive and therefore spends more electricity part is just getting activation. That's just piping in pictures and getting activations of those pictures is the most time consuming part, and that we can't really avoid. But all the other methods that I presented are relatively less involved.
Thank you. I was always thinking a little bit like you said, democratizing machine learning. I was yeah, that sounds great. And then my second thought was sort of, but it doesn't help if we're all dead. So this is this is not a criticism. That is more like just laying open what my train of thought was in that moment.
Yeah, no. I really welcome this type of thoughts because as a technologist, we often don't think about impacts of our work and what beyond your laptop, right? And I think pandemic and other things encouraged hopefully all of us to start thinking about this more carefully. What am I doing? How does that impact other people? How does that impact climate change? So I really welcome this question.
Sorry.
Thanks.
So to finalize, I think we have a participant that also raised his hand. So Joseph, maybe you wanna ask the last question, given that you already raised your hand?
Yes. Can you hear me?
Yes.
Yeah. First of all, thank you, Bim, for this nice presentation. I have just a question. I mean, about the topic in general. So, how do you think that interpretable machine learning can make machine learning models brought to sensitive fields like healthcare, economy, these types of fields that really do not tolerate machine errors? So maybe what I understood from today's presentation is that with interpretability, these I mean, machine learning models could be brought into these kind of sensitive fields. I'd like to know your comment on this part.
So are you asking that how interpretability can help with domains where the adoption is hard?
Exactly. I mean, decisions made by machines tend to not be forgiven like humans, for example, because humans can have they can explain themselves really and elaborate themselves in quite a good manner, but machines not. Yeah.
Yeah, I do think that interpretability is playing critical role in adoption. If you meet I work with doctors in my work, they have their ideas of what the right decision is and what the right explanation should be. And they are often right. Machine learning models could be wrong, and wrong for the right reason or right for the wrong reason and all sorts of things. By enabling this interaction, especially in the way that borrows the domain expert's language, like using diagnostic concepts instead of pixels, I think will facilitate this domain adaptation in a good way. Not just, we don't want to just convince them to use machine learning. No, that's not what we're trying to do. What we're trying to do is you decide as a domain experts, because you know the best, whether this model is worth deploying. Is it helpful? Is it a net plus? Only then, and if this interpretability method can show you that, then use it. Otherwise, just ditch it. Just go with your gut feeling, because you're still the best person to make this medical diagnosis.
Thank you very much, Bim. I think this is a good final point to close the discussion. Thank you, everybody, for attending today. Here, the claps, I can only do myself, so thank you, Bim, again for being here today. And thank you also to Martin, who is in the background helping us to run this without technical issues. And I hope you all enjoy the rest of the conference.
Thanks,
See you very
Isabel.
soon, hopefully again.
Yeah, thanks for inviting me, and everyone stay safe.